So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, in the previous class we have started an important concept called parametric process or parametric down or up conversion. We took a specific example and we try to find out if we launch an electric field with frequency 2 omega, whether it is possible to find out a field having a frequency omega. That means, is it really possible to find out some electric field having subharmonics, or the subharmonic generation is really possible or not. In order to find the subharmonic, we find there is a necessary condition, classically at least, there is a necessary condition that we should launch some kind of subharmonic wave in the input. If there is no subharmonic wave in the input, we will never get any kind of subharmonic classically. Then quantum noise is a process through which we can generate subharmonic, but also we find there is a important phase relationship, and if this phase relationship is such a way that exponentially we can generate subharmonic, then subharmonic will generate, and there is a possibility also that it will attenuate, because we will find some exponential decaying term is there because of certain phase conditions. And in that case, even though in the input we have subharmonic waves, which is the necessary boundary condition, but that subharmonic wave will not going to sustain throughout the distance and it will decay exponentially. So, we will start from that point. So, today it is class number 35. And today's topic is optical parametric amplification. We will continue with that, and we will study a special case difference frequency generation under optical parametric amplification. So, this is the slide that we have used in the last class, and we find that for subharmonics, delta is an essential parameter, which is the phase relationship between the two field E1 and E2, and this phase relationship suggests that if delta equal to 0, we have amplification, and if delta equal to pi, then we get attenuation. Now, if we look very carefully about this term phi 2 0 minus 2 phi 1 0, this term is not a very new term, because this phase we have already found when we were calculating something related to this theta. We find one very important constant, if you remember, that u2 u1 square cos theta was constant. So, this relation, we find that from this relation that theta was phi 2 minus 2 phi 1. So, exactly this quantity is here. So, it is coming in same way. So, once we have this delta including this term, then readily we find that this is some sort of phase relationship that we already got in the previous calculation. If I extend this thing, I think this will be clear. So, we have already this expression for amplitude, and this amplitude expression for u1 and u2 gives me that it is related to sin theta and sin theta. That time in the corner in the sticky note you can find that delta theta was phi 2 minus 2 phi 1, and we mentioned that if this value is plus minus pi by 2, then we will going to get this value was plus minus pi by 2, and for this plus minus pi by 2 we can have our expression u1 and u2 slightly modified. So, now here we can see that if I put delta equal to pi by 2 or delta So, let me write first in terms of delta what we had in the previous. So, delta was equal to phi 2 0 minus phi 1 0 with 2, then plus pi by 2 is equal to 0. And we say that when this equal to 0, we will get some kind of amplification. So, if it is 0, then from here we can say that phi 2 0 minus 2 phi 1 0 is equal to minus pi by 2. This pi by 2 will go to this side and we will get pi by 2. So, once we have this pi by 2 term, then please note that delta equal to minus of pi by 2. If I put this, then this quantity, this equation and this equation, if I look carefully, when put delta theta equal to minus pi by 2, sin pi by 2 is kappa u 1 u 2. So, kappa u 1 u 2 will be there, and sin pi by 2 with the negative sign become negative. So, this negative sign is going to absorb. So, we will have plus kappa u 1 u 2 for u 1. Now, if I only concentrate to this equation, we can see that u 1, if we say u 2 is a constant, then I can solve this differential equation, and if I solve this differential equation, you can readily see that u 1 is going to be amplified, because we have an exponential term with a positive argument, and that means it will exponentially going to increase if u 2 is constant. That was our assumption from the beginning, and this is happening because our phase matching condition, whatever the phase condition we have. So, this phase condition suggests that delta become minus pi by 2, theta become minus pi by 2, or delta in terms of pi 2 and pi 1, phi 2 and phi 1 become minus pi by 2. So, this is one condition. The second condition, let me write it once again, delta was pi 2 0 minus 2 pi 1 0, and then plus pi by 2, and we say if it is pi, then what value we will get from phi 2 0 minus 2 phi 1 0, this value is how much? Pi minus pi by 2. So, it is pi by 2. This quantity is our theta. So, eventually we will have theta equal to pi by 2, that means this term. When we have this term, then we can see that this equation and this equation become same, only a negative sign is appearing here. Because of this negative sign, if I do the similar process that we have done for this case, we will find that exponential term will appear here as usual, taking u 2 as a constant, but one negative sign will also be there. This negative sign suggests that u 1 will going to attenuate. So, that means this phase which is related to phi 2 and phi 1 is very important to excite or attenuate a particular field. In this case, we are dealing with the subharmonic fields or u 1, and we find that u 1 can be attenuated or amplified. Already we have seen in the previous class, but this is the equation that we had derived in 2 or 3 class ago. In previous class this equation was there, and using that 2 equation also we can come to the same conclusion, and you can cross verify that whatever the thing you have done is exactly the same thing we using these 2 important equations. Okay, so let me go back to the next important topic, and this is optical parametric amplification. So far we are dealing with a very specific case, as I mentioned, and that is the subharmonic generation. And for subharmonic generation, we are going to generate from 2 omega, we are going to generate omega. But in general, optical parametric amplification is defined in this way as shown in your screen. The optical nonlinearity responsible for second harmonic generation is also used to amplify weak signals. So, this optical nonlinearity is not only generate second harmonic generation, it also also leads to some kind of amplification of weak signal. The basic configuration involves an input signal at omega s that incident on a nonlinear crystal along with the pump. So, that means if I insert a input signal omega s and a pump omega p in the input, normally the pump frequency is greater than the signal, then we find the some sort of amplification is there for omega s. That means I am launching two fields in the input, one is omega p which we call pump, is a strong field, and with that we also launch another field we call omega s which is signal, and pump and signal are now together inside the system, and now inside the system we have a nonlinearity. Because of this nonlinearity, what happened? So, in degenerate case we find second harmonic generation may be there, but here we are not looking for the second harmonic generation. In general we use omega s and omega p. So, that means this is non-degenerate case. So, omega s will going to amplify. Now, omega s will going to amplify. Not only that, there will be another wave omega I, we call the idler wave, we call this as idler wave. So, this idler wave omega I, which is the difference between these two, will also get amplified. So, that means optical parametric amplification, there should be A here. So, in its simplest form involves the transfer of power from pump wave to frequency omega p, pump wave at frequency omega p to waves at lower frequency omega s and omega I. So, that means I launch omega p and omega s, omega I is generating inside the system, and the pump will going to amplify. The pump basically gives the additional energy to feed the corresponding field related to frequency omega s and omega I. So, omega s and omega I both will get amplified by the launching strong pump. So, for the lower frequency for second harmonic generation, we find that the lower power omega is fed by higher frequency omega 2 omega, that we have already seen in the previous calculation, that subharmonic is really possible to generate subharmonic if we put suitable phase condition. But in optical parametric amplification in general, we can also amplify lower frequencies which are non-degenerate in general. But when omega s and omega I are same, then it is basically the degenerate case. We call it a degenerate parametric amplification. So, degenerate parametric amplification we have already studied. The point is, we have already studied degenerate parametric amplification, and in the previous class and this class also we deal with the generation of omega frequency from 2 omega frequency, and this omega and 2 omega are basically they are the degenerate frequencies. To 2 omega frequencies are generated. So, that is why they are degenerate. So, now we will remove this degeneracy and try to understand what happen in general if omega s and omega I are not same, that means a non-degenerate case. Okay. So, let us understand this process in a more systematic way. So, whatever is shown in the previous slide, now this is pictorially it is shown here, that if I launch two waves, which is a strong pump shown here omega p, and with a signal omega s. So, omega p is a frequency of pump which is a strong wave, and omega s is a signal. So, inside this system under the OPA process or optical parametric amplification process, we can generate another wave of frequency omega u, which is a difference of omega p and omega s. So, since it is a difference between omega p and omega s, so this is nothing but the difference frequency generation. So, this is something different frequency generation, but how the difference frequency is going to amplify the field associated with the frequency, which is difference between two frequency pump and signal, how this field will going to amplify, or how the original signal that was there in the input will going to amplify, we will going to study these things in this particular lecture. So, under optical parametric amplification, as I mentioned, omega I is generating. So, that means the field that is generating is difference frequency field. In this energy diagram, things are more clear, that I am launching one pump omega p. This wave is already there, which is signal in the blue line. So, this signal get amplified. So, we will get two blue lines here, blue waves, which is at frequency omega s, and also there is a difference frequency, these and these, there is a difference frequency which we call idler, that is also generating. So, pump, the system absorb pump, and this pump, so if I draw this figure like this is pump with frequency omega, or in terms of field EP, it will going to generate two different waves. One is omega s, or in field S, and another is omega I, in terms of field it is EI. These two fields are generated, and these two fields now we will going to find out how these two fields are amplified, really they are amplifying or not, and there is a frequency relationship, and omega I is equal to omega p minus omega s. This is the energy conservation, this is coming from energy conservation. So, this is our structure, this is our structure. So, in the next slide we will do all the mathematics and try to find out really these two things will going to amplify or not. So, our aim here is to find out the previous slide, that omega p and omega s and omega I will going to generate from omega p, and whether these two things will going to amplify or not, that we will going to study mathematically. So, we will start with our old three equation. This is the equation of three different waves, pump, signal and idler. So, these three equation is a coupled equation, and in coupled equation we put two important approximation, and these two approximation is one, the pump is constant, that means we are launching a strong pump, and absolute phase matching condition is achieved. We start with the two important approximation, that the pump is constant and absolute phase matchings are there. So, when delta k is equal to 0, so we can say that this term and this term will not be there, that is one assumption. And secondly, in ES and EI, these two equation is important here. EP is sitting both the cases, and this EP will remain constant, that means we can treat it as a constant. So, we will basically discard this equation where the variation of EP was there. So, we will not going to take this equation, we just take this 2 and 3 equation and consider EP as a constant. So, using these 3 equation and considering delta k equal to 0 and EP is constant, we can find out the evolution of Es and Ey. So, if I see here Es, so ESZ can be written as this form DESZ, DES dz is equal to I d omega s NSC, which is this, and EP Ei star. We simplify this kappa s, because kappa s can take care of d omega s NSC, and d I dz is this quantity, which I write also in compact form with kappa. So, here we should write it is kappa I, this is not kappa s, both the cases it shouldn't be kappa s, it should be kappa I. So, when I write, when I differentiate this quantity once again, so we will have d2 Es dz, d2 Es dz. So, when I differentiate this quantity, EP is constant. So, we will have a quantity d Ei star dz, d Ei star dz I can replace from here, and when I replace I will have a negative sign here because I am making a star of that, and EP star and Es. This quantity should be Ei, this is a typing mistake, I write Es, kappa s. So, now these two terms can be written in this way. So, I minus I become 1, kappa s kappa I will be multiplied, and EP star. So, I will write mod of EP square and Es. Now, I consider one quantity G, which is G square is equal to kappa s kappa I and mod of EP whole square. So, this is my G. So, now if I put this G, we will have a differential equation that is having this particular form. So, this is not a very new kind of differential equation. The signal will going to have this kind of form that we know, because we have already calculated this kind of things in the previous calculation. Once we have the differential equation of the signal field, readily we can have the solution. Readily we can have the solution. So, we have, so in the right hand sticky note we can find that G square is defined in this way. Our differential equation is this. A direct solution, we know what is the form, because we are being using this solution for long, that Es is equal to A sin hyperbolic of Gz and B cos hyperbolic of Zz plus B cos hyperbolic of Zz. This is the most general form or the most general solution of this given equation. The next thing is that the boundary condition, and if you remember the structure, it is important to remember the structure. What is that? So, omega p was launched along with omega s. So, the field associated with omega s is not equal to 0 at z equal to 0. So, we should have some kind of signal field at z equal to 0. So, Es at z equal to 0, basically the signal at z equal to 0. So, this is the quantity at z equal to 0, I can put this value is B. So, B has to be equal to some input value, and we define this input value at ES0. This is the input. If now I put this value B, so Es become A sin hyperbolic of Gz plus Es cos hyperbolic of Zz. I just replace B to ES0. Next, the similar process we will going to use to find out the value of A. So, we will make a derivative. So, when we make a derivative Es dz, so we will have A g cos hyperbolic of Gz, and the derivative of this quantity is E is 0 g sin hyperbolic of Zz. Cos becomes sin hyperbolic become cos hyperbolic, and when I put z equal to 0, the entire quantity become A g. Now, ds dz, in the previous slide, if I go ds dz, this quantity is how much? This quantity is I kappa s E p E I star. When I find this quantity at z equal to 0, so we need to find out this quantity at z equal to 0. So, E p at z equal to 0 and E I at z equal to 0. But E I is a field, is a different frequency field. The frequency associated with E I is a difference frequency omega p minus omega s. So, at the input this frequency was not there, the field of this frequency was not there. So, if it is not there, so I can write E I at 0 equal to 0. So, when E I at z equal to 0 is 0, then the entire quantity has to be 0. So, A g is equal to 0 and this corresponds to A equal to 0 because z is a quantity which is not equal to 0. So, eventually we find that E s is equal to E s 0 cos hyperbolic g z because this quantity is not there, applying all these boundary conditions. Okay. So, as I mentioned, we find out what is E s, and E s is E s 0 cos hyperbolic of g z. That means E s is going to evolve some, it is non-zero at z equal to 0, but with z it can change, it can increase. So, once we have E s, then we can also find out E I because E I and E s are related to this equation. So, E s, let me write it here. So, if we remember d s d z was I kappa s E p E I star. So, if I try to find out E I star, then E I star will be simply this 1 divided by I kappa s E p d s d z. So, that means if I know my E s, then if I make a derivative, then this derivative gives me E s star g sin hyperbolic of g z and I kappa s E p, and E I star can be represented because now what I will do, that I will just write g s in terms of kappa, and so g was kappa s kappa I mod of E p square. So, it was g square. So, g was root over of kappa s kappa I and E p. We consider there is no phase associated with p, this is a strong pulp, and if it has a phase, then we can consider this phase has to be 0. Then we can simply write mod of E p square is equal to E p. So, if I write this E p will cancel out, and eventually we will have one term minus I root over of kappa I s E s star 0 sin hyperbolic z. So, once we have this E I and E s, then we can readily see that the corresponding intensity of signal and idler is proportional to sec hyperbolic square, there should be a square term, and sin hyperbolic square. Again I am making some mistake here, so please note, because E is proportional to cos hyperbolic. So, I which is proportional to mod of E s square should be square of this. So, when we have a square, both square term, and if I plot as a function of z E I and E s I s and I, then we will find that the curve is something like this. So, that means both of them are increasing, both of them are amplifying, and this is amplifying because they are getting some kind of power pump, that power from some kind of energy from the pump power, and as a result we will get some kind of amplification. This kind of amplification is called the parametric amplification. So, we have studied the parametric amplification for difference frequency generation, that means for omega I. So, in the next class we will do the similar kind of approach and try to find out what happened if I generate some frequency generation under optical parametric amplification. So, for optical parametric amplification, how the sum frequency is going to generate, we will study in the next class. So, thank you for your attention in this class. So, see you in the next class and thanks.